All right. So I want to finish the conceptual node introduction by talking directly a bit more about Node. Relatively short conversation here, this may seem strange for those of you who aren't familiar with JavaScript programming or asynchronous programming, or just have never seen something like Node before. At first, this conceptual presentation of computational processes and architecture may not make much sense at first. But I do want to go through it. I do want to present it as yet another alternative after the ones we just reviewed, and use it as a reference point. I'll keep coming back to there's just four slides left. But I'll keep coming back to them throughout our conversation on Node to remind you of what's going on behind the scenes. And we'll talk a lot when we talk about performance and scalability. In any event, we left off here last time, right? We had talked about some of the pros and cons of different forms of legacy web application architectures. Again, CGIs, server-side scripts, slash implicit invocation, in this container component model, right? Going from heavy processes to a many threads in a thread pool behind this single big Java process, and talking in a very distributed way in a big backend, that enterprise class backend that we talked about, right? This whole mess right here. So again, what folks in No Community basically said is, you know, this whole thing, how about we just don't do it, right? Let's try and do something simpler. Let's go back to a simpler, more well, I wouldn't call it obvious model, but can we go lightweight? Can we avoid some of that deployment complexity, that operational complexity? Can we simplify the programming model? And that's where Node.js comes in, right? The asynchronous processing model is what I'm going to talk about it now. Um, the notion that we are using JavaScript, which means you can use the same language and some of the same tools at least in the browser and on the server. And again, we'll talk a lot about how there used to be this clean separation between front end development and back end development, but now full stack development has definitely blurred the lines of where functionality and even behavior or code lives. Different functions live in your application. So, this whole client server strict roles thing is kind of, the lines have been blurring in web development for the last few years. And then, past to advanced deployment or newer styles of deployment architectures like containerization and microservices. Talked a little bit about those last time. That's an advanced topic. Maybe by the end of the semester we'll revisit those and try and understand why those are important. But those are some newer both business and technology cases for organizations, and this approach is easier to do. Take advantage of these new methods. So anyway, let's get to it. What do we mean by this asynchronous process model? Well, the first thing is, and I'm going to focus on this diagram up here first. We are talking about a single threaded model. So before I talked about a thread pool, right? Now we're talking about a single thread. Say, okay, you're talking about a single process and a single thread. How does that scale? How is that better? Well, we're going to talk about that. Let's talk about how this model can work and how can it scale. How can this model scale if you're processing all in a single thread? Well, some of the keys here. There's some assumptions about the way you code and the way that you process things in this model. You assume that processing is done in a non-blocking, quick computation fashion. I'm going to talk about that more in a second. But the whole point is incoming work. All right, these are client requests. So these are HTTP requests that turn into work. By that we mean it's an HTTP request that asks you to invoke some kind of dynamic behavior, a program, a computation on the server, just like all our other programming models do. But now that work is essentially put in a loop or a queue, right? As an event, as a piece of work to pick up and do, right? If the CPU is not doing anything, then it's woken up and told by the OS to do something. But if it's busy, then essentially your work is put in the queue. We'll talk a little bit in the coming weeks about how to manipulate that queue. But for right now, it's like, you get in line. But the point is you got to be very quick. All right. The presumed is that you're going to round robin your way through this work. Okay. Now, What happens in a single-threaded model if your computation isn't quick? What happens if you have a blocking call, right? So we talk about things, and now I'll start talking about here. Things like, when your program makes a call out to the file system to read a file, right? You're communicating to an I/O subsystem, and typically that call is done in most programming languages and most models of sequential execution as a blocking call, which means when you issue the read call, you sit there and wait. You wait till that data is read off a disk, brought back in through the I/O subsystem and into your memory space so you can perform computation on it. In this model, that kind of blocking behavior is bad because the CPU just kind of sits here and does nothing, right? It's just sitting there waiting while it's executing your process. Now, we know in an operating system may swap out your process and bring in another one to keep the CPU busy. But just in the context of your single application, if you do it that way, you're basic, and you do it in this event loop. So let's say that this is a read task, and that is one of the pieces of work sitting on this queue of work that's hanging around. All right. Well, if this is what is being processed on that queue, if you issue a blocking call, then the CPU over here can't go and get the next work and go do something in the context of that application. All right. So the point in an event loop, it's the hamster on a treadmill concept. You've got to keep that hamster running and healthy. It's got to be running through work. It's got to be running through tasks to do from a computational perspective that are discrete, small, and quick. If they're big, if they block, then we have a problem. There are some facilities in the system. So yes, over here you see non-blocking workers, a notion of a thread pool. That is because, yes, there, and you see it down here as well. This is a different view in this bottom diagram of the similar thing. We have multiple requests coming in. We have our event loop or our event queue on a single thread, and it can delegate off to these POSIX is a computational standard for asynchronous thread behavior is used, and so you can do non-blocking I/O to stuff. You can delegate off long-running tasks to stuff, and so forth. All right. That's because blocking requests are bad, but sometimes you can't avoid them. You try to avoid them in this computational model. You don't want to program it this way, but maybe sometimes you can't. So if we can't, we can delegate them off to this infrastructure over here, which is a bit more the traditional infrastructure. Meaning there are ways to work with threads and so forth. But even then, when you delegate off to threads, the stuff you get back winds up on the event loop. All right. So the real point is what happens, and I'll draw in 4 colors. Is we have one request coming in. We have a second browser's request coming in. We have a third coming in, and we have a fourth coming in, right? These requests all share the same single thread. Okay, single process, single thread, which means they've got to basically take turn. Something's got to, in essence, round robin, through these guys, and that's what this event queue represents. All right, is that round robining, basically taking turns, right? And again, have this concept from an operating system perspective in a time sliced operating system. Now we're applying in the context of a single process running on the server, the JavaScript, the node process itself. All right. So understanding that there's that event loop there, understanding that it's a single threaded, will impact the programming model in ways that are far more significant than, say, over in the Java servlet model or in the PHP model. There, the computational model isn't quite as apparent to the application programmer. But in Node, you really need to be aware of what's going on, and you need to be aware of how many other Node applications might be using the same process, or how many other different requests can come in and be processed. And you really have to understand the nature of their computational profile to work effectively. But let's look at this from the perspective of what Node will then do versus what a traditional server does. In traditional server, I'm basically going to say something that is like a Tomcat, our Java model, or anything that is thread pool based. I mean, we could be there is such a thing as process pool based. But the real point is, in most traditional servers, each incoming request, these are HTTP requests, as I've said before, are processed by having a certain fixed number of threads. So in this case, this diagram is showing us 4 particular threads of processing. Now, of course, in a real server, you're going to have hundreds, if not several hundreds, depending on the computational scalability of the box you're on. But simple example, we have 4 threads that we want to work with. So the first 3 requests come in, they each get a thread, and whoever comes in first wins. A 4th request comes in, it grabs a thread, but then this request comes in and it blocks. It has to wait for the resource to be freed up, or any of these resources to be freed up for that matter. All right. So it's going to sit, if you have more concurrent requests coming into a thread pool based server, you're going to have, whatever the overflow is, basically standing in line, waiting. All right. Now, how's that different in Node? Node has no up or down bound like that because it has a single thread, so it's not pooled. Now, what this diagram kind of trivializes is the fact that that single thread has to keep busy. That single thread, I like to think of this guy. I wish I could draw one, but I'm not even going to try and draw one because I'm horrible at it. That's your hamster. All right, that's your hamster. That hamster is, how do you draw a hamster? So I told you I couldn't draw. He's running like crazy on the treadmill, and he's got to chew through all that work. That's a different model. This is a ticket window model, right? You're a ticket buyer, and you're coming in, and you're waiting until the next window's open, right? You're waiting in line. Next window open, you get serviced, all right? And you hang on to that window, right? As well, we should mention, until you're completely serviced. If you got, multiple orders to make or something like that, and you take longer. I know I've been to Chase Field and Diamondback games, and I get in a wrong line, right? And you're sitting there waiting until that person's business is completely done. Think of a ticket window in the Node.js model. There'd be one ticket window, and you would have a discrete task, and the person behind the booth would handle that discrete task. So the first discrete task might be give them your will call reservation ID number, right? As soon as they get it, though, you have to go back to the back of the line. You got to go back in the back of the queue. Well, the next person comes in and they service and say, okay, here's my will call reservation number. And then by the time you make up to the front of the line, you could say, well, was my callback ready? Did you find my will call reservation? All right. If so, now I'd like to make a change to my tickets and maybe purchase another one because my kid brought a friend. Okay, I'll make that request. I'll get back in the event queue. Right? You go through the event queue multiple times. In this model, in our traditional model, no, I'd sit at the window and have that conversation with the ticket officer until I'm completely done and satisfied, and I'd walk away. Right? But that can be a long-running computation. So that's the key to Node scalability, is this ability that's always chewing through the work. And if you're programming discrete elements of work and everybody in the Node server is well behaved like that, I don't have all the thread context switching overhead. Not huge in threads, but it's non-zero. I don't have multi-process like in CGIs and implicit invocation and other models where I may be context switching from an operating system perspective. I'm in one process with one thread chewing through work. All right. As I mentioned before, the biggest thing for us is going to be, if you haven't programmed this model before, getting used to the asynchronous programming model and the pseudo multi-threading that goes on. So that's where we'll start. But the key is programming in a well-behaved way so that hamster is well fed and running at a nice constant speed, so to speak, getting through the work it needs to do. All right. This, by the way, if you are a mobile developer, this really isn't that different from how Android works, right? That's why you have a single app and a screen at a time. There is a certain round robining that goes on to service requests, all right? Now, of course, in any round robin algorithms, there's typically usually ways to game the system, make your work appear first. There's ways to prioritize work and so forth. We will talk about some of those fine-grained details, but honestly, it's really about understanding the event queue, this computational model, the profile, and programming in a well-behaved way according to the best practices. Okay? Overview, I'll return to these concepts over and over, But next session, we're going to start getting in this code. We're going to start talking about how you do these things. We'll start taking a look at the code in the asynchronous model and how that kind of looks, and then we'll go from there and revisit these concepts as we go through the code.